Hello guys, we're back with I have put the generator in a case, and one thing I wanted to say, this will be basically, I'll upload this later, but this is going to be basically the finalized schematic. I didn't mess with this resistor. I played with it a little bit, but then I was going to have to play with this load resistor, which then was wanting to shift this a little bit in a way I didn't like. It was going to take quite a bit of changing, and then plus I was getting problems with some of the voltages here. So I think for the time being it's better just to leave this at its value. It runs the voltages a little bit lower on the plates on all the three tubes, but that's okay too. As you can see, it's not a bad waveform. So this is at the high end, which is around about 57 megahertz. The very low end is around about 2 megahertz, a little over 2 megahertz on the lowest band. Of course, nothing's going to match up to a dial. I just put a dial on there. But I'll discuss that here in just a little bit, what you can do about dials and things of this nature. But it is working. It does like being in the case better. That gives it full shielding. I tried applying shielding in some other areas, and that was kind of causing some problems there too. But she is working, and working not too bad actually. A few things I wanted to go over that had came up in the comments a little bit. One was, I threw something at you that you probably, I have never mentioned or said anything about before, and that's this tube, this half of the 12AT7, the cathode follower. So I thought maybe I would do a little bit on it. They're really a nice little circuit, and real simple. Anyway, I went ahead and put up something here, and basically this is just basically a cathode, what the cathode follower is. Another name for it is known as a common plate. Most amplifiers you deal with, or what you run into and you see, is called a common cathode, where you input into the grid, between the grid and the cathode, and your output is between the plate and the cathode. And that's your your standard operating tube, like this, where the cathode basically goes to ground, probably maybe through some resistance, maybe directly ground, whatever. You pull power out of the plate, you feed into the grid, standard tube. Well, that's called a common cathode. But the cathode follower is known as the common plate. And now, in reality, there's your B plus is in here. Your supply voltage to the plate. I just left it out for clarity. But you feed a signal in. It feeds in between the grid and ground, and you pull out the signal between the cathode and ground. So similar to a common cathode, with some minor things, differences. You see here where I've got V1 equals VG plus V2. V2's output, V1's input. VG is the voltage on the grid. It's the voltage taken to bias the grid up. So V1 appears to be greater than V2, and that's one of the characteristics of a cathode follower. The voltage gain is less than 1, less than unity. So there's no voltage gain, but there is a current gain, a power gain. These provide a considerable amount, very good increase, very excellent power gain and amplification. So they're used in a lot of circuits where you're more interested in getting power out and not so much interested in getting voltage. The other thing, well, we'll just go through some of the good points. They have high input impedance. Works great for this circuit here. We don't like to draw or load down our oscillator, so we want to feed it into something that has high input impedance, as Z is impedance. So that way we don't load it down very much. But it has a low output impedance, which is great too, because you're feeding the signal into, you know, radio, whatever. You're going through a coax lead that's going out there, which is probably 50 ohms. So you want to match that up pretty close. You want to keep your output impedance fairly low. That way, that's also gives you your power gain right there. Is where the power gain comes from. They have excellent, I put good, but they really do have excellent wideband frequency and phase response. They're an excellent amplifier that covers a wide range of frequencies and don't really care. They'll do fine at low frequency, medium frequency, high frequency. They just do great at it. Their output phase is in phase with the input. Not a big deal on a signal generator, but sometimes these are used for inputting in audio circuits where you've got a Class B push-pull or Class AB push-pull. These can be used as drivers in cases like that where you've got a phase splitter circuitry also involved in that circuit. You want to make sure you're keeping your phases the same where you go through your driver. Voltage, again, like I said, is less than 1. Good power gain. The other nice thing is the input capacitance on the input of these tubes on this tile is reduced. So that's very helpful when you're dealing with frequency, dealing with like a signal generator or something of this nature. Now, for those who want to go, now this is great. You don't want no math. Here's where you stop at. That's basically the circuit. That's basically how it works. You just feed in. All this is here is just your signal being applied into your grid resistor. RG is just the grid resistor. So the signal's applied in series with the grid resistor, feeds into the tube, and runs through and feeds out to our RL here, which is our load resistor, whatever load we're putting on it. Excuse me. Now, for those who want the math, want a little more deeper into it, here's the equivalent circuit. Generally, when you're doing design and doing your math for it and doing your figures and figuring out circuits, you don't generally work with the circuit as is seen on a regular schematic drawing. You work with what is called equivalency circuit. Now, I didn't mark anything. I've showed these before, but this is the grid here. This is the same point here is here. This here is this point. And this point is this one here. So, your plate connection, this is plate, this is cathode. This little bit in here is what the tube actually does. We have a plate resistance that's inside the tube. There's a certain amount of plate resistance that's in the characteristics of a tube, always given in there. A lot of times on the characteristics sheet it won't tell you that it's R sub P, but plate resistance is this right here. So this is for the 12AT7, same tube as in here. So plate resistance, which varies with whatever plate voltage is on it, but from 15,000 to 10,000 ohms. But that's all RP is plate resistance. It's in the characteristics. Mu is the amplification factor. Mu is nothing but your GM times which your transconductance times your plate resistance. I went over this in a previous video. And VG is the voltage that's being actually applied after the grid resistor. It's the actual true voltage that is going into the grid. So mu times VG, mu times that voltage, VG here, going through the plate resistance, then we get your output. And V2 is our output across our RL. Now, voltage gain is V2 divided by Vn, V1, which is Vn, will equal mu times my RL, my load resistance, divided by mu plus 1 times RL plus RP. You just plug in the numbers, you'll have mu, you can figure out mu, your RL is whatever your load resistance will be, and RP you get also from the characteristics, and you can figure out your voltage gain. It will always be less than 1. The resistance input into the amp, into this cathode follower here, is infinity, basically. It's just infinite. It don't draw anything. It's the grid. You're going into a grid circuit of any tube is got extremely high input resistance. Your resistance out is RP divided by mu plus 1, and that gives you the output impedance of the tube. For the 12AT7, I actually figured it up at the plate voltage it's running is roughly about 247 ohms output resistance. Input resistance is virtually infinity, so there's drastic difference. It don't load the oscillator down at all, and the output fits into basically when you work up the voltage dividing circuitry through here. By the time you get here, we get a good matching circuit to that, and so we get the maximum flow out of signal. The power gain is more complicated formula, and it's 4 times mu squared. Just take mu squared times RL, which is the load resistance, times RG, which is your grid resistor, whatever bias resistor you use. And then that's divided by this quantity here, mu plus 1 times RL plus RP. Take that entire quantity and square it. That'll give you the power gain, which generally works out pretty decent power gain. So anyway, for those who don't like the math, this is basically it. We feed it in, just a standard circuit with a grid resistor, feed it in, it comes out the cathode. The main important things is you get high input impedance, low output impedance. You got a good wide frequency response. Your output's in phase with your input. Your voltage gain will be less than 1, but your power gain will be quite high. And then if you're really worried about some input capacitance in your circuit, because you're dealing with frequencies getting in there where you got to worry about that, it is reduced on this type of amplifier. For those with the math, there it is. So anyway, that's where we're at. I've got another little video I'm going to make. It has nothing really to do with this, it has to do with something else, but I'll get to that here in a little bit. Anyway, I'll probably be uploading both of these at the same time, roughly at the same time. I tried once trying to upload more than one video exactly at the same time, and it really was real slow. So anyway, that's where it's at. Now I want to work out a parts listing and stuff, and I'll get that all put together, and then I'll put the two up. Oh, I wanted to talk about the scales. I mean, I just had something here I wanted to put on here and just to get some numbers. But I generally, for one thing, I don't ever really follow these. That's why I've got this here. And the main reason is it's easier to see up here. Even though this thing's calibrated so that when it's on, like say 400 right here on this scale here, it's 400. But if you notice, you know, you can move that a little bit, and depending on what angle you're at and everything, if you're not directly over top of it, you can be off quite a bit. And the other thing too is, especially like with this one, it doesn't have a mark for 455. There's 455. Same thing with 10.7. If he's wanting to do that kind of alignment, you know, it'd be right about right in there. Well, that's real difficult to try to judge exactly where that's at. So when you got a scales like this, even if the generator is dead accurate, it's real difficult to try to get, you know, some of these frequencies you can get in here, and just the slightest little movement, just like that, can make a world of difference in your frequency. And so that's how come I like having a frequency counter, because now I got a digital readout. I can use this scale to get it, you know, like if I want 455, you know, I can get it, you know, okay, I'm pretty close, and then go down here and tweak it until it's right on 455. But what about if you want to make your own scale? Well, you know, you build a generator and you can either use a wheel like what's in here, or you can, this actually probably be easier to make something up like this. And there's various ways, but what I suggest to do instead of doing any type of math with it is get you like a protractor or something that you can get some generalized marks on there temporarily, and then start at the low end on your lowest band, the lowest end, and take, you know, like a frequency counter, a scope or whatever, to see where the frequency is. You know, you may tweak it a little bit to get it to a nice round number if you want, or whatever, but, and then certain points along the way, get another shot. You know, maybe the next, even, let's say you're wanting to run in here, like on this band D, you know, 2.7, maybe the next one would be like 3. Maybe the next one you might say, okay, 3.5, I can write that down. I can write 4 and then 5 and then just go single digits all the way through. And then you can put in as many different little middle marks as you want. And you just go through all your bands, picking some relatively whole numbers and marking them on a piece of paper that you've kind of temporarily stuck on here on your faceplate. Get them marked out. Then you can also then work out your, you know, your various knobs, your output, whatever, you know, labeling and stuff, and how you want to you know, set them up, all marked on that piece of paper. Scan it into your computer. Use, you know, like, what is it, Paintbrush Pro or whatever. There's various different programs that, you know, work with graphics and artistics and stuff, and work you up something that's a lot nicer, you know, maybe even with, you know, colors and whatever, and where it looks really neat. And any inkjet printer, and of course LaserJet printer, can print what they call transparencies. Those are the old overhead projector plastic piece paper that was used on those. You know, when you, back in the old days, for those who are older anyway, before we had computers and all that stuff, we had overhead projectors, and the teacher would take these plastic transparencies, put on there, and she could rock, you know, they'd already have stuff printed on them, and she could write on them or whatever. Well, you can print those. You can buy that stuff and print those off in your printer. Now, with the inkjet printer, you want to make sure you let the ink dry really good. You know, before you ever print off some test sheets on regular paper until you get it exactly the way you want it, and then print it off on one of those. Let it dry good. Put I don't know, like a clear lacquer or acrylic or something over there to protect the ink, and then work out a means of either glue it on your back plate. If you glue it, make sure it's some sort of glue that is very, will dry very transparent, and get it put on there, and then you'll have your scale, and you'll have your power on and off, your modulation, whatever you want to call them, and your attenuator and so forth, and you'll have that all figured out. So anyway, this video is getting long, so I hope that helps with the questions on the cathode follower and stuff. And I want to thank for some of my new subscribers I've gotten, and I thank you guys for comments and stuff. I will answer some of them, try to anyway. Been rather busy doing some other stuff too. I'm working on I'm working on the signal tracer deal that originally was meaning to be calling it, and then I have been also working on the chassis for the radio, and I have decided that we're not going to stick with just one radio. We'll probably build a couple different styles. So anyway, I'll be doing another video here shortly that'll go up tonight too, that has to deal with something else. So, and then we'll be getting to working on that signal tracer. So anyway, I'll get this stuff up in parts list and stuff and everything, and here in the next day or two. So thanks for watching, and I'll see you on the next video.